This is the notes for section 3.9, step functions. If you haven't done so already, make sure you stop the video and read the section before continuing on. First of all, let's define what a step function is. So when we talk about a step function, here's our definition for it. It's a piecewise linear function whose graph looks like a series of steps. Okay? Two types of step functions are floor functions and ceiling functions. These are the ones that we're going to look at here today in this particular lesson. So first of all, let's describe what a floor function is. Okay, and it's basically when we're looking at a floor function, there's two other names that we use for it: the greatest integer function, and the one that is the most descriptive for us, and that's the rounding down function. When we write the floor function, we write it with kind of two brackets, with the brackets just on the bottom showing kind of the floor of the function. And basically what it does is it takes all numbers and rounds them down to an integer. Okay, so it doesn't matter what the number is, it's always going to round it down until it gets up to the next integer. So like a 3.5 would round down to 3, a 3.9 would round down to 3, but once you go above 4, then it rounds to 4. Okay? The ceiling function kind of does just the opposite. When we talk about the ceiling function, some other names for it are the least integer function, and once again the most descriptive one, which is the rounding up function. Now when we're using the ceiling function, we notate it like this with kind of brackets showing the ceiling, and it's the least integer greater than or equal to x. So when you think about the ceiling function, what you're really going to do is you're going to be rounding up. Okay, so floor function rounds down and ceiling function rounds up. So let's take a look at a couple of quick examples involving the floor and ceiling function. So if you look at part A and B, both of those would be the floor function, so we're going to be just rounding those down. So if I look at 6 2/3, I'm going to round that down to 6, negative 10.01. Now if you think about that, we're going to round that down. So if you think about it on a number line, here's negative 10, here's negative 11. It's between negative 10 and negative 11, so I'm going to round it down. So I'm going to round it this way. Therefore, it's going to be equal to negative 11. For C and D, we're doing the rounding up. So if I have the ceiling function of 2 pi, that's the same as the ceiling function of approximately 6.28. And we're going to round that up, so it's going to be equal to 7. And then finally 27, it is already an integer, therefore the ceiling function on it would just keep it as that integer of 27 as well. So next let's take a look at the graph of a floor function. So if I'm going to graph a floor function, what we're going to do is there's going to be an open circle, and it will be on the right. For ceiling functions, if I'm graphing that, the open circle will be on the left. So open circle is on the right for floor functions, and it's on the left for ceiling functions. Okay? So if you think about it, if I'm going to graph this, every number between negative 3 and negative 2 will round down to negative 3. Therefore, the value of that function would be negative 3 for every single value between that. So if I look at that graphically, that means it's going to be a horizontal line. And here's an example of that. A horizontal line from just going across from negative 3 all the way over to negative 2. It's an open circle at negative 2 because that's when, as soon as we hit negative 2, the graph is going to jump up to the next one. So that's why with the floor function, that open circle will always be on the right hand side. In example 2 here, you can notice that I'm just going to graph the ceiling function, and it looks exactly like the floor function, really, except for the fact that now my open circle is on the opposite side. So instead of it being on the right-hand side, it's on the left-hand side. So if you think about all the values between -3 and -2 on this one, those values are going to round up to -2. Okay? So as you can see, they're all at -2 here. Okay? So that's what the graph of the ceiling function would look like. Alright, finally I'd like to take a look at an application of a step function. And we have a situation with a taxi here. It says suppose a taxi rate is an initial fee of $3 plus 60 cents for each full quarter mile traveled. So they're only going to charge you for a quarter mile if you complete that full quarter mile. Okay? It says write a formula for T of M, the charge for the trip of M miles. Well, the way I can do that is I'm going to write it like this. I'm going to start out by saying, okay, well, no matter what, he's going to charge me $3. And then I know that they're going to charge me 60 cents for each quarter mile. So if M represents the number of miles, each mile I'm traveling 4 quarter miles. So I'm going to use 4M in terms of the value that I'm always rounding down. So remember that it has to be a full quarter mile before I actually get charged that 60 cents. So it will round down to the nearest quarter mile if I do it this way. So this is the function that I would want to use. Now part B says, well, what is the charge for a 2.9 mile taxi ride? Well, now all I'm going to do is I'm going to take that 2.9 and I'm going to plug it in for M. When I do that, I'm going to work inside of my floor function first. So 4 times 2.9 gives me 11.7, which I can round down then to 11. Okay, which makes sense because that would be, we wouldn't quite make the 12th quarter mile. That we'd have to actually go 3 miles before we get to that 12th quarter mile. That's why I'm only being charged for 11. Then I'm going to take that times 60 cents plus 3, which would give me my total cost of $9.60. You make sure you want to get that work down in your notes, and then we can talk about any questions that you might have about that in class.